So in 8.1, we started talking about this thing called a confidence interval, which we use to estimate plausible values for a parameter, for a population parameter. So we went through a lot of vocabulary, kind of talked about how to construct it. Today we are specifically going to talk about confidence intervals for proportions. So there are some conditions. There's 3 conditions, and there's always 3 conditions from here on out till the end of the year. Whenever we do a confidence interval, a hypothesis test, there's always 3 conditions to check, and they're pretty much the same. How you check them isn't the same, but the 3 that you check are all the same. So you always check for random, you always check for 10%, and then the third one is either called large counts or normal. So either one of those is what you're checking for. So random, it needs to say somewhere in there that it's random. 10% when you're sampling without replacement, which means you're just taking something out, you're not putting it back into the population to choose to recheck. You need to check your 10% condition. We've already been kind of dealing with this. Remember, this is the one that I prefer. So you do 10 times your sample size has to be less than or equal to the population. And then large counts are normal. You have to check to see that n times p hat, which is your sample proportion, and n times 1 minus p hat both have to be at least 10, so greater than or equal to 10. Now, we do have a little wiggle room with that number. So if you don't get 10, if you get like 8 or 5 or something like that, it's okay. You may just want to proceed with caution, so you may get some surprising results. Okay, so here's a quick definition. For some reason, we are switching from not for some reason, for a good reason, we are switching from calling something standard deviation to standard error. Standard error is when you have multiple things. So remember when we did our sampling distributions and we said no longer does a dot mean a dot, but it means a sampling or a statistic from a sample. That would be you would be calculating the standard error, not the standard deviation. Okay, so just note pretty much those 2 words are interchangeable, but standard deviation is for when a dot means a dot. Standard error is when a dot means a summary statistic of a sample. Okay, so single dot means single item. Standard error, a dot means the summary statistic of multiple items. Okay, so here is your formula. So first you check your conditions, and then once your conditions have been met, here's your formula right here. You take p hat, which is your sample proportion, and then you add and subtract that to a z-score. Remember, a z-score is an exact number of standard deviations away. It's also called a critical value. I'm going to show you what those are in just a moment, times the square root of p hat times 1 minus p hat all over n. Now let me break this down for you a little bit. We learned in the last video that p hat is called your point estimate. That is the number right in the center of your interval. So that's your point estimate, then you add and subtract to get the endpoints of your interval. That z right there, that's called your critical value. This square root, that's your standard error. Remember, that's very, very similar to standard deviation, but it's standard error. And now just to note too, this whole second part here, so after the plus or minus, that's called your margin of error. So to get your confidence interval, we saw this in the last video, you take your point estimate and you add and subtract the margin of error to it. And your margin of error is made up of a critical value and a standard error multiplied together. Okay, so what are these critical values that you will use? These are the most common ones right here. So 85% not used a ton. Your most common are going to be your 90, your 95, and your 99. I would jot those down somewhere, or you can always just Google them if you forget what they are. If you remember last year, we did an Algebra 2. You constructed confidence intervals, and you used, I believe, 2 as your z-score, and we never really explained why. That's because that's the number of standard deviations away you would be for a 95%, and we estimated 1.96 to be about 2, but it's really 1.96. Okay, last 2 things. We're going to do 2 examples. when you're constructing a confidence interval or a hypothesis test, but today we're just talking about confidence intervals, we always go through this process of state, plan, do, conclude. State, plan, do, conclude. If you do those 4 steps, I know that you'll get everything in there that you need. In state, you just say what you want to estimate and at what confidence level. The plan, you need to identify the appropriate method and check the conditions. If the conditions are met, then you perform the calculations. The do part is everybody's favorite. Most people hate the state and plan. The do and the conclude are pretty easy. That's where you get the math and the numbers. And then your conclude is you interpret. And again, you're going to use my words to interpret. So I'm going to go through a whole process with you. Before I do that, I've given you all reference papers. If you turn to the inference summary section, if you look at the top here, there's your state, plan, do, conclude for confidence intervals. It tells you exactly what to do and what to include. Here's the how to construct a confidence interval right there. So today we're going to be using this state, plan, do, conclude, this confidence interval. And then it also says there's like a proportion over here. And then this is a one sample. It's an estimate. And there's your formula right there with your conditions over to the side. So if you ever are unsure, just go over to this reference paper and you can check there and it's got everything that you need. Okay, so here's the example that we're going to go through. It says Miss Quinn's class took a simple random sample of 102 pennies and discovered that 57 of them were more than 100 or more than 10, that'd be cool, more than 10 years old. Okay, so we want to calculate that confidence interval. So we're going to do the state. We wish to estimate the proportion of pennies that are more than 10 years old. I forgot to include in there at a 99% confidence. So if you went back up to the top here, it would tell you in the state you need what parameter you need to estimate and at what confidence level. Okay, plan. You need to name your test. It's right here, one sample z interval for p, one sample z interval for p. You need to check random, normal, and independence. And they're all right there. So random, it said it was a simple random sample. 10%, you do 10 times your sample size, which was 102. That gives me 1,020, and that is less than all pennies. So we are safe to assume independence. And then last but not least, we need to check normal. Normal, you do your n times your p. My p here, I figured out in the next step, so I just added it in there. P hat would be 57 over 102. So if you read back up here, it says 57 out of the 102 were 10 years old. That's my p hat. Using a calculator, I got that was 0.559. So if you do your sample size, 102 times 0.559, you get 57. And then if you do 102 times that complement, so the complement of 0.559 is 0.441. Those two add up to 1. If you multiply that, then you get 44.92. Since both of those numbers, the 57 and the 44, are greater than 10, we can assume normal or that it's large enough. Okay, do. Calculate your p hat, which I already did. Plug it into the formula. It's p hat plus or minus a z-score. Now, we are doing 99%. So if I scroll back up to here, z sub 99 is 2.58. I think I just Googled this instead of scrolling. So I used 2.576. That's perfectly fine. That's the z-score that corresponds to a 99%. Times the square root of p hat, 1 minus p hat over n. Where did I get that formula from? Right here. Or I did give that back to you in the first part right there. Okay, so you can look either place to get that formula. Then the worst part about this is typing it on the calculator. Please do that slowly so that you don't make mistakes. You would hate to get this far and then just make a silly calculator error. If you plug it in all correctly, you should get 0.432 to 0.686. And then to conclude, again, use my words. We are 99% confident that the interval from 0.432 to 68.686 contains a true proportion of pennies that are 10 years or older. And then part B says, is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? And the answer to that would be yes. And that's because 60 is in the interval. Okay, so because 60 is in the interval, that is plausible. Last thing, sometimes we want to work backwards and we want to figure out what our sample size would need to be for a desired margin of error. So what I do is I take my margin of error equation. Again, I had showed you that up here when we wrote out the form for a confidence interval for a proportion, your margin of error is after the plus or minus. So the z times the square root, p hat times 1 minus p hat. So there it is, margin of error. And we want it to be less than or equal to whatever value I have. Now, this is really important. If they don't have an estimate, if they don't tell you a proportion, use 0.5. Okay, so some of you are going to forget that along the way, so you may want to star that. Very rarely do they have an estimate for the proportion, so just assume 0.5. It is the strictest proportion that you can use. Okay, the last example, probably the most mathy you're all going to get this year. So suppose that you want to estimate the true proportion of students at your school who have tattoos with a 95% confidence and a margin of error of no more than 10%. So on that previous slide there, we saw that it is z times p hat times 1 minus p hat all over n, and that has to be less than or equal to the margin of error. Now it tells you your margin of error of no more than 0.1. So there's my margin of error. It had told me nothing about the p hat and the 1 minus p hat. So if you read through that, there's nothing about that. So I assumed 0.5. N is what I'm going to be solving for. And we are at a 95% confidence. So if you scroll back up, 95% is 1.96, which is where I got that z-score of 1.96. Okay, so start in the purple here. That's the equation without doing any math. Now I need to start to solve for n. So the first step when you're solving for n is you need to isolate the radical. So get this radical by itself, and I'm going to do that by dividing both sides by 1.96. So if you look over here, I divided both sides by 1.96, and I got what's in the green here. So the square root of 0.25. I also multiplied 0.5 times 0.5, which got me 0.25. So square root of 0.25 over n, that's all in the square root there. It looks like it got cut short, but it's all underneath the square root, is less than or equal to, and then 0.1 divided by 1.96 is 0.0512. Now I want to get rid of that radical. So to get rid of the radical, you square both sides. If you square both sides, the radical is now gone. So that gives me 0.25 over n is less than or equal to 0.002603, which is 0.05102 squared. So got rid of the radical, squared that side. Then I did a little cross multiplying here, or butterfly method, if you know what that is. So basically I multiplied both sides by n to get the n up here, and I divided both sides by the 0.002603 to get that down there. If you divide that out, you get 96.04 is less than or equal to n. I like to read the n first, so I just switched it around. N has to be greater than or equal to 96.04, which means n has to be 97. Okay, so that's probably the trickiest part. I don't think constructing a confidence interval is tricky, but sometimes working backwards, especially with knowing how to work with radicals, since it's been a little while, that's a little more tricky. So in this video here, we talked about proportions. In the next video, 8.3, we will be talking about means. I think I've mentioned this before, that from now on, it pretty much goes proportions, means, proportions, means, proportions, means, and so forth. So now we should be able to construct a confidence interval for a proportion using state plan do conclude, so that we do not forget to name our test and check our conditions. And we should also be able to figure out what the minimum sample size should